Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I'll show CFD heat transfer analysis, parametric study and optimization of a plate type heat exchanger. This analysis optimization will be done by SolidWorks flow simulation. The model is already made using SolidWorks. Let's see this model. This is the model actually. See, it is transparent view. We'll change the transparency and see the original model. Let's see that original model. We're changing the transparency to the original one. This is the actual plate exchanger, right? This plate heat exchanger is consisting of different parts. The middle one is known as the main plate. We are having 4 different types of gaskets. This is the front gasket and this one is the end gasket. In between also we are having 2 different types of gaskets. This one is the forward gasket and this is the backward. So alternately we are arranging all these things, right? Let us see the parts one by one. It is very important to see the main plate. See, a front side and back side is actually different, right? Important to understand this plate. Hot water will flow along this way. By the same time, this area is reserved for this hot water. When hot water will be passing through this surface, this hole will be closed by the N type jacket. So we are alternately creating 2 different surfaces for hot water and cold water. Similarly, from the back side, cold water is passing through this one. By the same time, it is taking this surface also. And during cold water passing through this surface, this hole and this hole will be closed by the front gasket, right? This is actually front type gasket. Water will be passing through this one and water will go in the forward direction. By the same time, it will pass in this area also, right? This region is separated and along this region cold water will be flowing. Okay, this is known as the front or forward gasket. You see another type gasket. This is backward type gasket. In this case, what will happen? Cold water will be passing through this one and this area also it will be covered by this cold area, right? And 2 more are there. This is the end gasket. Both hot water and cold water will be passing through this one. At this end it will be stopped by this wall. And last one, you can see the front gasket. This is the front type gasket. From this one hot water will be passing and from this one cold water will be passing. This is the hot water inlet and hot water outlet. This one, this is cold water inlet and this is cold water outlet, right? The back side you can see some space is there for hot water. When hot water will be passing through this inlet, it will go along this direction. At the same time, it will flow radially also in this region, right? It's better to see the assembly. Yeah, this is the assembly. So I'll explain here. It is very clearly. From this end, hot water will be passing along this direction. By the same time, along this plate, some space is there. It will flow in this area also. If we cut this, then it will be clear to everybody. If we cut along a specific plane, maybe we want to cut this one along top plane. Okay, see. What will happen is hot water is passing through this one, right? And when passing, it has some gap. Here it is. It will pass along this area also. Again, this is the cold region is. That means alternately we are having hot and cold regions. Now it is very easy to understand. Hot water is passing through this one and cold water is passing this one, right? So first one, when hot water is passing through this end, we are having some space. It will flow along this area also, right? Again, it is closed at this end. That means here hot water cannot pass through this area again here it is some gap is there, that means again hot water pass along this way and it will pass along this way also, right? Let us go for analysis for it, right? This is our model. It is a plate type heat exchanger. It is having high efficiency because it is very compact and it is having large surface area also. Let's do analysis, right? Okay, this is the model. The leads have already been created. 4 set of leads are there. This is the entry of hot water. This is the exit of hot water, and this one will be entry of cold water, and this is the exit of cold water. Okay, right. Now first of all, for starting this flow simulation, we have to create an environment, and that environment can be done using wizard, right? Default name of the project is project 2. Next, we are considering SI system and temperature will take in degree centigrade. Next, it is an internal analysis. We will take heat conduction in solids, and by the same time we want to take gravity. And you can see very clearly that the direction of x-axis is actually this way. So gravity we are considering along y-axis, right? So we have to provide gravity along y-axis minus 9.81 meter per second square, and along z it will be 0. Okay, next. So we are considering liquid water at different temperatures, so we have to take water only. Next, we're going to see that metals, 2 different types of metals we are considering. The plates are consisting of copper metals, and the gaskets are made up of different, that one will be provided later on. The default outer wall thermal conditions and roughness values we are considering. Then initial conditions you have to select. Let's select that initial temperature of atmosphere equal to 30 degrees centigrade, and solid temperature will take same as 30 degrees centigrade. Finished. Now you can see the computational domain, this is there. Now you can see here that these leads are actually out of this domain, right? So what you have to do is the domain size you have to increase a little bit. We can edit that domain in which these leads should be inside that domain. Other parts also we are making a little bit more dimension, that is all the parts of this model should be inside this domain, nothing should be outside. Okay, done. This is our computational domain, that is this domain is responsible for all these calculations. More the domain, time for calculation will be more, so we have to reduce that domain also, right? Done. Now our domain function is done, we have to hide it, right? Done. Very good. Now what a very important thing is water particles, hot and cold, both will be passing through this model, and it is better to make this model transparent for better viewing of these water particles. So this model, all the parts have been selected. Now let's change the transparency. It is a transparent model right now, so we can clearly view water particles from here, so right? Done. First of all, we have to see that fluid subdomains, that means from which path hot water will be passing and from which path cold water will be passing, that to be clearly identified. Now for identifying those region, better to see the segmented view of this model. We are cutting this one from the top plane. Okay, Now hot water will be passing to this one, right? This is the hot water inlet. So fluid subdomains, insert fluid subdomain. To define type of water, we have to take water at 90 degrees centigrade. We will be passing through this end, right? Done. This is the hot water fluid domain, right? Done. Again, you have to see the cold water domain. You can cut it and move it a little bit down. You have to cut from the. So this is not needed necessarily. This is very important to show the location. That's why we are cutting. We can do this one in a different method also. Fluid subdomains, insert fluid subdomain, and here in this case cold water will be passing, and the temperature of cold water will be 10 degrees centigrade. So this is the domain for cold water. You can see the domain. These two are completely different domains, right? Both are separate completely. Okay, done. Next one, solid materials to be defined. We have already defined this main metal copper. We have defined. We have to see again, insert solid material, predefined metals, copper. I told already, main plate is made up of copper. So you have to select the plates. All the plates have been selected and it is made up of copper. Material specified. Now for the gaskets you have to specify the material. Solid material, insert solid material. Actually these gaskets are made up of rubber, high quality rubber, nitrile rubbers are there. So in this case we will select as polymers. Let's select the gasket made up of Teflon. Actually these gaskets are made up of high quality nitrile rubber. Select Teflon for this all gaskets. All the gaskets have been selected. It is made up of Teflon. So material is defined properly, right? Next one we have to apply the boundary conditions. For applying boundary condition in a proper way, it is better to select the segmented view. You can cut it from the top hot water inlet, right? So this point is working as a hot water inlet temperature, right? Boundary conditions, insert boundary conditions, and mass flow rate. We will select mass flow rate as 0.01 kg per second, and thermodynamic parameters, you can see the thermodynamic temperature will be 90 degrees centigrade. That means hot water is passing through this end at 90 degrees centigrade. Done. And again, as cold water will be passing from this bottom place, and this one will be acting as the exit end of the cold water, right? Here also we can apply this boundary condition. Boundary conditions, insert boundary conditions. Now it will be atmospheric pressure at this end. This is for the cold water outlet. Okay, select that one. Done. Now what to select for the cold water inlet again. So you have to cut it along the down plane. Let's move it down. Got it. Now we have to apply cold water inlet location here itself, right? So we are applying boundary condition again. Boundary conditions, insert boundary condition. Mass flow rate will be again same 0.01 kg per second, and thermodynamic parameters, its temperature will be providing as 10 degrees centigrade. Cold water we are providing at 10 degrees centigrade from this location. Done. Another location is there. This means this location. This one will be working as hot water exit. So boundary conditions, inside boundary condition, it will be hot water exit location. It will be environmental pressure at this location. Again check. Done. All the boundary conditions have been applied properly. Now let's see the complete view of the model. Right? Okay. Next one, we have to define some goals. Let's make the lids visible. The lids are now visible. Now we can apply our surface goals. Insert surface goals. When you see average temperature of fluid at the exit of hot water, select other, lid number 41, go and check. Another surface goal we want, goals, insert surface goal, again average water temperature at the exit of cold water end, select other, lid number 40, done. Two surface goals we have defined. Now another goal we want, equation goal. Insert equation goal. That will come from previous goals. We want to take the difference of these two, average hot water temperature minus average cold water temperature. You want to see. This is hot water temperature exit end minus cold water exit end temperature. Okay, this is defined. So all the goals have been defined properly. Now we can run it. Let's run it. It has started running. Now you can see the solver window. From the solver window itself, we can see our results. It is preparing the model. Mesh refining is going on. Now it is being prepared for iterations. It is about to be started. Yeah, number 1 iterations has started. Number 2 is going on. Now we can watch the results. Better to see in the form of graphical views. We see all the goal plots. That means we want to see both hot water and cold water exit temperature. By the same time, we want to see their temperature difference. Okay, let's see. Now see, the top one is actually hot water exit end, and the green one is the cold water exit end, and in between this is the difference in between these two. Hot water exit end initial temperature was 90 degrees centigrade, and cold water exit end initial temperature was 10 degrees centigrade. As time is approaching, so cold water exit temperature will be increasing. By the same time, hot water exit temperature will be reducing. It is going on. Let these iterations move on. We'll analyze when it is coming to the end. The solver window has finished its calculation. You can see the results here itself. Like the initial temperature of hot water was 90 degrees centigrade, and finally after 127 numbers of iterations, the final temperature of hot water has come down to 80.348 degrees centigrade. You can see at the end, and exit temperature of cold water equal to 23.152 degrees centigrade, and the equation goal, that is the difference between the exit ends of hot and cold water, equal to 57.19 degrees centigrade, right? So before getting the results, we saw it from the solver window. Now we can do one thing, like we have to see the different cut plots and result analysis a little bit. We can see the results. First of all, we'll see the cut plots. Insert cut plots. We're going to see cut plots from front plane. Let's see it. This is the pressure. We want to see temperature of fluid. Cut plot 1. Edit definition. We want to see for temperature of fluid. Again check. Right, this is along the front plane. Now it is better to see in the form of an animation. Cut plot, clear and hide. Cut plot, play. Let's see in the form of animation. It's better to see if we see in the front plane. Like it can be analyzed that we can see different set of colors as it is approaching from front to end. This is the hot water entry end and this is the cold water entry end. You can see different colors across different planes, right? So at this end, temperature of hot water is very high in the range of red zone, that is 90 degrees centigrade, and while coming down its temperature is reduced in the range of like 58 to 60 degrees centigrade in this range. Okay, and for cold water also, this is the inlet of cold water. It is in the range of 10 degrees centigrade approximately, and while coming out its temperature is in the range of green zone, that means 49 degrees centigrade. It is changing approximately at different places, its value is changing. Now we'll do one thing, we can see these cut plots along other planes. Cut plots, clear and hide. Cut plots, edit definition. You want to see with respect to some other planes, right? We want to see cut plot with respect to our right plane. Let's see that one. We'll see from right side exactly. Okay. Now it is very clearly understood that we are having different like temperature region. So when hot water is passing through this way, it is red, and when coming down, it is color is different. That means it is color is yellow, different temperature. And also this is the hot water region, this is the cold water, again hot and cold, alternately hot and cold region we can see, right? If we see this one in the form of an animation, cut plots, play. So the thing is, like hot water is passing from here, it is temperature is red, and again it is going along this way. So alternately hot and cold water temperature distribution we can see. First one is hot, second one is cold water, right? Let's clear and hide this part. Next one we will see surface goals, surface plots, insert. We're going to see all surfaces, temperature of fluid want. Let's see temperature of fluid along all surfaces. It is very clearly understood that hot water is passing through this way, and by the same time it is passing across these cross-sectional areas also, right? It is red, that means hot water. From this side also we can clearly see this is the hot water region and this is cold water. Again, this is hot, this is cold. Alternately we have created hot and cold water region, right? If you see from that side, this is the cold water region. So this is cold water region, this is hot, again cold, hot. This way it is moving on. We have created different sets of hot and cold water regions, right? Okay. Next one, we will see the flow trajectory. So clear and hide this part. Flow trajectories, insert. The numbers, instead of 20 we will make it 200, and going to be in the form of arrows only. You're going to see temperature of fluid, right? So what we'll do is to select the path, we'll select the entry of hot water and entry of cold water both. So select other, lead number 42, and again we have to select the cold water inlet, select other, lead number 40, green check. Now we can see the flow trajectories, flow of hot water and cold water together. See, this is the flow trajectory, right? If you see from this right side, this region is for hot water. It is going along this path, by the same time it is passing along this surface, and this is cold one, again this is hot water. So alternately hot and cold water regions you can see, right? Better to see this one in the form of an animation. So flow trajectories, clear and hide. Flow trajectories, let's play it. You can see clearly hot water passing through this path, by the same time it is passing through different planes, right? And the planes of hot water and cold water is completely different. Because of conduction only, the temperature of cold water is rising, but there is no mixing of fluid. Let's see this one from cold water end, this side. All the paths are completely different. Only the temperature difference between hot and cold water because of conduction. Because of conduction, temperature of the surface is going up, and that surface is responsible for increasing temperature of this cold water. Okay, you can see from front plane also. This is the flow trajectories. Okay, done. Next one, we have to see the results. So flow trajectories, clear and hide this part. Now we'll see the results. So goal plots, insert goal plots. We're going to see all the goals. Show that these results we have already seen. We can better see this one in the form of graphs from history. So it is telling that initial temperature of hot water at the exit end was approximately equal to 90 degrees centigrade. Then it has come down after 140 numbers of iterations. Its final temperature is 80.4 degrees centigrade, right? And similarly for cold water temperature also, initially it was in the range of approximately 10 degrees centigrade, and finally it has gone up to 23.148 degrees centigrade, right? And this is the difference of temperature of hot water and cold water exitants. Initially the difference was very high. Initially the difference was 81.85 degrees centigrade, and finally after all these iterations the temperature difference between hot water and cold water exitants is equal to 56.85 degrees centigrade. So we have a goal to make this difference of temperature to be 50 degrees centigrade. For this we have to change some input variables, right? We'll do this one later on. Now next one, we have to go for some kind of parametric study. That means with different input variables we'll find out our goals. Okay, let's go for this parametric study. So solve new parametric study, and in new parametric study you have to go for design of experimentation and optimization. So in this case we have to take some input variables. The input variables may be in the form of dimensions, or it may be in the form of our boundary conditions, initial boundary conditions. We'll select initial boundary conditions. Let's take the boundary conditions from here. For changing the results, we have to depend on this mass flow rate. We can change the temperature also, but we are planning to alter the mass flow rate only, right? So what can you do? We can either increase the mass flow rate of 1 or decrease, or we can change the mass flow rate of 1 and 2 both. We'll change one parameter. Let us increase the mass flow rate of cold water. Okay, we are selecting mass flow rate of cold water. You can check, and the range we have to specify right now. It was 0.01 kg per second. We'll make it 0.05 to 0.5 kg per second. We are increasing the mass flow rate of cold water, right? Let's see within this range what will be the output goals. Output parameters that are dependent on goals. You have to select all the goals. Now let's see the scenarios. We are selecting 5 set of experiments with 5 set of input variables within our specified range. We want to select our goals. Let's create that scenario. There is 5 scenarios we have created. With different input variables, we'll get our output goals or our desired results, right? Let us start this design study, run it. For design experimentation and optimization, the solver window has finished its iterations. We can see the results right now. With the different input variables of cold water mass flow rate, we got our goals. Mass flow rate was ranging from 0.05 kg per second to 0.5 kg per second. Within that range, we found that at 0.3875 kg per second, our equation goal, that is the difference of temperature in between the hot exit and cold exit temperature, is equal to 61 degrees centigrade. And at mass flow rate 0.1625, the equation goal is 55 degrees centigrade. And when the mass flow rate is high, you can see the temperature difference is also high. When the mass flow rate is very less, you can see the temperature difference between the hot water exit and cold water exit is reducing. So from this one we can have an idea that our goal to optimize the temperature of this equation goal to be 50 degrees centigrade, we have to reduce the mass flow rate, right? Increasing the mass flow rate is not reducing the temperature difference. So we can understand from this experiments, to get our optimized 50 degrees centigrade of equation goal, we have to reduce the mass flow rate. Okay, This is all about today's parametric study and analysis of plate type heat exchanger. Instead of stopping it here, we can do something else, like optimization also can be done. That means by selecting one of the input variables, we can specify a targeted goal, and targeted goal can be achieved with that specified range. Because of time stringency, we are stopping it here. We can do this any other time. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.